Primitives in 3ds Max are mathematically defined templates of commonly needed simple physical object models. They start with very basic objects such as a sphere, a box, a cylinder, a tube, and so on. And they extend on into the more esoteric objects such as a capsule, a Gengon, torus knot, doors, windows, and many more. Let me show you some of these primitives now. I can go into the control panel up here, and you can see we've got standard primitives as the creation option at the moment. You also have extended primitives here. So let me just create some of these standard primitives first. I'm going to create a box first. So pretty much all of these, they're all drag and drop. So just define the base of the cube. Let's create a cone. Drag that out. Pull in the end of it. A sphere. I'll just turn on base to pivot here. There's a sphere. Let's do a geosphere. Base to pivot's turned on. Do that as well. A cylinder. A tube. A torus. Go. Pyramid. A teapot. And a plane. There we are. Those are all of the standard primitives. And then if we move on, we can look at the extended primitives. Things like the hedra. Let's choose that there. And for this, you can actually choose different types of hedra. We've got a torus knot. Quite a complex curved object that curves in on itself. We've got a chamfer box. There you go, and you can actually change the fillet by adjusting this value here. Turn on shaded so you can see it more clearly. There's a chamfer box. Chamfer cylinder. Same kind of deal. Change the fillet there. And the fillet segments there. Make a nice smoothed cylinder. Oil tank, capsule, so on, so on, and so on. You've got a lot of different primitives in 3ds Max. Now, pure polygon modeling is just fine. And when you're working on a more organic model for film and television and games, it's common for sub-D modelers to build most of the topology by hand using polygons. But in most circumstances, even sub-D modelers like to start off with a basic object from which they can build on, something like a cube or a cylinder. And if you're producing a model of a more technical or a mechanical nature, why bother to build a sphere or a cylinder laboriously by hand, polygon by polygon? I mean, it's pretty insane, isn't it, really? Because instead you can, with a few mouse clicks, as I've just done in the Max viewport here, build the object directly in the viewport using click and drag in, as I said, just a few seconds. And as I said, primitives are mathematically defined as inside 3ds Max, there's a simple spline patch based template for each of the primitives featured in 3ds Max. All of these objects you can see here and these other objects that we haven't actually shown yet. And these patches are simply 3 or 4-sided areas that are made up of mathematical curves. You can think of them in a way as being like a polygon, but these patches are made up of vertices and curves rather than the vertices and straight edges that you see in a polygon. These curves allow a patch to define a complex curved surface in 3 dimensions, and by combining multiple patches you can define quite complex surfaces and objects. Now, another feature we get from creating surfaces from patches is the idea of there being a coordinate space along those patches. If we look at a quad patch, we have effectively 2 axes. We can treat the bottom edge of the quad patch as one axis, and we can treat the left edge as the other axis. We can then treat the surface of the patch like any graph that we've seen when working in math. The bottom edge we call the u-axis, and the left edge we call the v-axis. And there's also a third implied axis, which is the one that runs in and out of the surface, and this is called the w-axis. So we now have 2 coordinate systems in 3ds Max. The first is the x, y, and z, and we use that for object, and world space. And we now have another coordinate system called UVW. And this is used to deal with the surface space of an object. And this may sound a little esoteric, but why do we need U and V? Well, those new coordinates allow us to define any point on that quad patch surface. And the same system can also be used for a tri-patch. We effectively treat it as a quad patch that's been split in half along a diagonal line. It still has two axes along its edges, bottom edge and left edge, and it also has another axis going in and out of the surface. And we still call these axes UVW. It's exactly the same as a quad patch, basically. And these UVW coordinates can be used for a number of purposes. But the main ones are for the definition of a point along one of the axis curves. And also by using two of these curves together, two coordinates, the U and V, we can also define any point on the surface. And we can use that point to define how we take a 2D bitmap and we translate that onto the 3D surface of an object. So we use these UV coordinates when we're actually texturing an object with a 2D bitmap. So these quad and tri-patch mathematical curve-based definitions mean that each object can then have each of its surfaces tessellated to the level that the user has specified via certain parameters for that object. Before we continue, let's have a look at one of these primitives, in this case a sphere, and at exactly what this tessellation means. And we'll just pick a sphere, just create one here, and we'll just look at it in wireframe for now. The word tessellate is derived from the Latin word tessera, which literally means four-sided, and was a corruption of an earlier Greek word. In the Roman period, a tessera was usually a small square of bone or wood, which was used as some form of token. But the main use of the word in Latin that we know it as today was a small square of ceramic, which was usually colored, and these were used to make up a mosaic. In computer graphics, tessellation is a process where a mathematically defined patch surface is evaluated and a polygonal mesh of tris or quads is created based on that surface definition and the parameters that control how the tessellation takes place. If you look at the sphere that I created, you can see that it has been tessellated into a number of triangles along the top here. This may not be that easy to see, so let's just zoom in here. You can see it's been tessellated into triangles along the top, and it's also been tessellated into quads along the sides here. Now, as I said earlier, the quads themselves are actually made up of tris as well. So, in fact, the entire surface of the sphere is made up from triangles. Now, the actual placement of all of the triangles and quads that you can see here is based on the mathematical description of this sphere. And here you actually have the tessellation value, and it's called segments in this particular case. And if I just put that down to 0, this is the most basic representation that 3ds Max can make of the sphere. As you can see, it's just made up of triangles, and it makes this diamond shape. Very, very basic. So as we increase the tessellation values, it adds more subdivisions along this curve. And what it does is it tries to approximate the sphere in a more realistic manner. So you can see it's adding in more subdivisions along this axis. And if we look at this axis, you can see it's adding more subdivisions around this axis also. So basically, well, this is U around this axis here, around the equator, and V along here, it's adding more subdivisions every time I increase this value. And as it goes upwards, with it adding more and more subdivisions along U and V, it gets closer to a decent approximation of a sphere. We'll just increase this value very quickly now. And when you get up to quite high tessellation values, as you can see, you get a pretty decent approximation of a sphere. And what I've been showing you here is the most basic form of tessellation that takes place on a surface, and it's called non-adaptive. And what this does is it takes a surface and it subdivides it based on the parameters that you've supplied to it in a linear manner. So for instance, if we look at a primitive box, let me just create one here. I'll just get this sphere and delete it. I'll just create a new box view here, drag this out. There we go. Just draw it by hand like that. And you can note that if you look over here, you've got length, width, and height segments. And each of these is a tessellation value. And by default with a cube, you can see that the tessellation value is 1. As you can imagine, it's pretty obvious how the cube is made up. It's made up of 6 quad patches. Here's a patch here. And as I said earlier, that the patch is actually made up of mathematically defined curves. Now, in this case, they're lines. They're not actually curves, but it's the same principle, basically. And we're using one iteration of tessellation. And what that means is it places one control point at each control point of the curve. So basically, it places a vertex here on one control point of the curve, another one here, another one here, and another one here. Then what it does is it creates a polygon based on that. Now, as the default mesh type in Max is edit mesh, it uses tries to do that. So it basically creates a try from here to there. So you've got one try here, and you have another try here. Obviously, it may not be that exact orientation. It may be a try here and then another triangle here. Depends on, how it actually tessellates that surface. But basically, if edit mesh did support true polygons, it would build the surface out of one quad. Now, if you use a tessellation value of 2 on the cube, and let's do that right now in all axes, we'll just pop that up. Max now places one mesh vertex at each control point of the box, and one equidistant vertex between the two in each dimension. So along these curved edges here, it places another vertex here, which is halfway along the curve, another vertex here, halfway along the curve, and another one here. So you basically end up with 4 quad faces per patch face. And if we then increase the value to 3 in all 3 dimensions, as you can imagine, very predictable what's going to happen. You've now got 3 points along here. You've got one here, here, and here, and obviously one here. Remember, with a tessellation value of 1, you still have 2 vertices here and here. When you increase it to 3, you effectively get 4 vertices. 1 at the beginning, 1 at the end, and 2 in between. We've got 9 quad polygons per face, and as this is an edit mesh, it's still actually made up of tries. So in fact, instead of 9, we have 18 polygons here, and each one of them is a try. So we can actually see that by, if I do this procedurally, I'll actually put an edit mesh modifier on here, go into edges mode, and then select, and there you are. You can see all of the actual triangles that make up this cube now. But 3ds Max is trying to represent it as quads, basically as a viewport speed up method, and also to make it look cleaner, basically. But underneath, as it's an edit mesh, it really is made up of triangles. And you can carry on like this, and the subdivision and finer tessellation of each patch will continue in a predictable manner. If you have a quad patch, i.e. a patch with 4 control points and 4 edges, you will get predictable quad polygons during tessellation. So if I get rid of this modifier and increase tessellation, we'll go to 9, 9, and 9. There you go. You've got completely predictable tessellation. You know exactly what you're going to get. And in this case, because the surfaces are made up of quads, you're getting quad tessellation. If the surfaces were made up of tris, you would be getting tri-tessellation here. It would actually be using triangles to do it. Now, as I said, this display here is actually a pseudo display. Underneath it's using tris, but you get the idea that what I'm saying. It will actually subdivide up quad patches into quad subdivisions and tri patches into tri subdivisions. This form of tessellation is used on our primitives, and it can also be used on patch and NURB surfaces, either in the viewport only or also at render time. It's a useful system as it's very fast to calculate, and also it gives the end user, you, a very predictable and stable result. You just dial in the tessellation parameter that you want, get it to the level of tessellation that you're happy with, that you need to model with, and you can just go on from there. You've got a pretty good idea of how it works. You're never really going to be lost in how it's going to tessellate, and it's basically the standard method that we use while we're modeling. And the second form of tessellation, which is something that we're not really going to look at in any great depth in this DVD or this series, in fact, is adaptive tessellation. And adaptive tessellation is a more advanced system that only really comes into its own on curved surfaces or on surfaces that are being tessellated further by a rendering engine to facilitate a geometric displacement during render. In primitives, adaptive tessellation involves a patch being evaluated for its level of curvature, and this is both in U and V directions, and a parameter defines an angle threshold for the surface curvature. The system then starts at, say, U0 and moves along the curve, and when the specified level of curvature is reached, the system creates a mesh vertex at that point and resets its curve measurement. It then continues on along the surface until the threshold of curvature is met again, and then it adds another vertex at that point. And it keeps on going in that way, basically tessellating up the surface based on the curvature threshold that you've defined. And in this way, the surface is subdivided along U and V directions, and this produces a grid of subdivisions that is densest in areas of the highest curvature and is lowest in areas where there's little or no curvature. It then uses this subdivision or mesh grid to create a polygonal mesh. So it then tessellates based on those subdivision values that it works out. A related system is sometimes used for extra tessellation doing a rendering to improve the quality of the surface geometric displacement. The original geometry is kept by the rendering engine, and a copy is made of its mesh for the displacement process. This copied mesh then has its vertices displaced based on a bitmap, and then the angles between each pair of faces on the mesh are compared, and if the angle exceeds a certain value, that face is subdivided along the shared edge's direction. This continues until all of the angles on the mesh are compared and tessellation is complete. Then the render engine displaces the newly created vertices in the displacement mesh to the correct height above the original mesh based on the displacement bitmap. You now have a new mesh and displacements that are much closer to an ideal approximation of the displaced surface. The angles are then re-evaluated between the polygon pairs, and the polygons are subdivided further if it's needed. So basically, if the angle between two faces exceeds the value, it gets tessellated again. And this process repeats until either a number of iterations has been reached, or maximum polygon count has been reached for that mesh, or possibly both. Some systems use a combination of both to define a cutoff point where it won't actually tessellate any further. And when this counter or polygon count level is reached, the adaptation stops and the resulting mesh is ready to be rendered. So in both cases, the tessellation of the mesh changes depending on certain parameters. With a patch, if the surface becomes more curved due to it being bent, then it may actually tessellate the surface more, and you'll end up with a different number of polygons on it. And the same thing can happen for the render time adaptation as well. If you change the angle threshold and you do another render, you may find that instead of a mesh having 500,000 polygons, it may have 2 million or 4 million polygons. So again, the polygon level count changes based on parameters. So it's an adaptive tessellation system based on the parameters that you define. Now, when you're modeling, you'll be working with a non-adaptive tessellation system all of the time. As you can imagine, an adaptively tessellated mesh would in fact get in the way of modeling. I mean, it's like holding an object and trying to change it whilst it's shifting around and changing its form in your hands while you're trying to do so. You really don't want that. You want to make changes to an object and for them to stay in that state until you make further changes. So let's go back to our primitives now and have a look again at how tessellation works, and I'll just use a couple of more primitives to give you an idea of how tessellation actually works in practice. Okay, so I'm going to create two primitives here, two spheres, and we'll create a sphere first. These are actually both spheres, but this uses polar coordinates and this actually uses a geodesic system. So we'll create one sphere here, let's draw it here, and I'll create this other sphere over here. Doesn't really matter where it's placed. And I'll just modify their radii. Let's just make this one into 30. And make this one into 30 as well. Now you can see the basic difference between these two primitives is that they use a different tessellation scheme. This one uses poles, and as you can see, it basically tessellates along U and V. And this method, or this one over here, uses a geodesic system pioneered by, I think it was Buckminster Fuller. And you can actually increase the tessellation, and as you do so, you can see it just decreases the size of the triangles, and you end up with a denser and denser polygonal mesh. You may wonder why they've supplied these two different meshes in Max. Well, it makes sense in that this particular method of tessellation actually needs more polygons to give you a nice spherical edge. This method here actually can use less tessellation and give you still a pretty decent spherical edge to it using less polygons. The downside to the geodesic system is that it doesn't really have a border, whereas on the sphere it does. And this allows us to actually create hemispheres. So you can actually change this value here. And as you can see, it's actually making a hemisphere. If I choose 0.5, it will actually make half a sphere. It actually matches the name. But you're not just stuck with hemispheres. You can go for anywhere in between, really. I mean, you can just change that value to be whatever you want. And you've also got two methods of changing the tessellation. One is you chop. So basically, you don't increase the tessellation as you go towards a hemisphere. And the other option is you squash. So you keep the same level of tessellation, but you squash it into this parameter space. So let me just show you this option. So there we are with the zero hemisphere. And as we increase the hemisphere value and it goes towards 0.5, you can see the subdivisions basically remain constant, but they get squashed into a smaller and smaller space. So basically, as you do this, it gets more and more detailed in the remaining area of the sphere. If we go back to chop, you can see it would actually keep its level of detail. So again, you've got two different options there. And the other option you've got with the sphere is you can also slice it. So let me just show you that. That allows you to create segments of a sphere. You can see here. So, and you can change this other plane too, so you can define exactly how this works. And also you can see you've got these creation options, base to pivot. If I turn that off, that then puts the pivot point in the center of the object. The other option obviously is to put the pivot to the base of the object. So if you want to create spheres that lie on your plane here, you can just turn on base to pivot, and then you can actually define them so they sit on the plane. So as you can see, you've got the option of creating hemispheres using the sphere, and you've also got the option of slicing it, as you can see here. So you can create exactly what kind of subdivision you want of a true sphere. And you only have those options with a polar definition of the sphere, because I mean, you can see the way the actual surface tessellates. It works very nicely with the tessellation method, whereas, for instance, slicing wouldn't work very well on the geodesic dome. The other options you've got with the geodesic dome is you've got other types of tessellation. You can go for octa or tetra in the way it actually tessellates, but generally I leave it on icosa. You put it down to the lowest level. That's the most basic tessellation that you can do of the geodesic dome. And as you said, as you increase the tessellation, you get closer to a true approximation of a sphere. So as you can see, we have the same mathematical primitive, a sphere, but two different methods for constructing it from polygons. And as a result of those two methods, we have extra options on the polar sphere. So tessellation, or the method of tessellation, does play an important role in the final makeup of the primitive. So let's have a look at a couple of more primitives now. Let's have a look at a torus, for instance. Here we go. Just click here. And there we have a torus. So here you can see we have options for the outer radius of the torus, the inner radius of the torus, which basically changes the cross-section from here to here. We can rotate exactly where the tessellations take place around the circular circumference here. We can twist, as you can see. There's a twist point here. So we can actually create a twist along the length of the torus. Just put that back to 0. And we can choose how many segments we want along the length of the torus. Just put that back up to a high value, and along the circular cross-section of the torus. We can change the tessellation in that way. We can choose if you have smoothing on, and again, the same kind of thing as we saw with the sphere, we have the option to slice the torus. We can choose a start point and an end point, so we can choose exactly where and how the torus is sliced. And again, we can turn that off just at the click of a button. So you can pretty much get the idea of how primitives work. Basically, there's a drag and drop system. Let me just create a teapot to show you that. You click where you want to place the primitive, then you drag outwards to define whatever parameters that it is that actually creates that primitive. In this case, it's the radius of the teapot. And there we go. There we have a parametric teapot. It's made up of patches. There's various patches making up this part, making up the body of the teapot and the spout, and also the lid area. And if I put it down to the lowest value, you can see, there we are, that's the most basic tessellation of the teapot. And as I increase the tessellation values, you can see it gets much closer to a true approximation of the teapot. You can see that the primitives in 3ds Max are pretty varied in their makeup and have different areas of usefulness. For instance, this teapot, this may seem like a strange option to have, but it's useful because it's what I would describe as being a complex object. And it can be useful for doing test renders, or if you're learning how to use the dynamic system in Max, you can try out a pre-built complex object by using the teapot. The teapot has got complex curves on the lid area and also on the body, and it can self-shadow itself because of the spout, which you have here, and also the knob on the lid and the handle. And it also has elements that branch off from the main body of the teapot, and this makes it useful for testing out things like ray tracing. If you want to see how the teapot actually reflects itself, then it has elements, you know, the spout and the handle, which will allow you to do that. And for that reason, the teapot is actually quite useful as a primitive. Generally, you're not going to be using it to create actual models, unless, of course, you need a teapot. But it is useful for other purposes, as I said, doing render tests and dynamic tests and so on. And that shows you one of the flexible features of a primitive. It can be part of a model, or it can be for any other purpose that you want, really. But generally, you're going to be using primitives to form a part of a model, a larger model. And in many cases, the primitive itself is not going to be the final word. You may add other primitives to it, or the primitive itself may be exactly what you need for the model. As an example, if you can do a model of the Earth, basically you create a sphere, you put a texture on it, and there you have a reasonable model of the Earth. Now, obviously, if you want to get in there and have a little bit more detail, like if you're going to zoom into an area, then you start getting complicated and you'll have to actually model the terrain of the planet. But when you zoom out from the Earth, when you're in space looking at the Earth, for all intents and purposes, the actual height of mountains compared to the actual size of the Earth means that basically the surface of the Earth appears to be completely flat. So you can basically use a sphere to represent the Earth. So in that case, the primitive is the finished model. If you're creating a cube, then basically a cube primitive may do the job for you. It has mathematically perfect edges, so it isn't necessarily perfect, but then again, you have the chamfer cube, which was one of the extended primitives, and that could be used to produce a perfectly good cube for most purposes. And you can also deform primitives using the very many modifiers that come with 3ds Max, which is something that we'll look at a little bit later in this DVD. And you can also use space warps to do the same kind of thing, to form some kind of deformation on the surface of the sphere, to twist a cube. And you can do that on multiple objects at once very easily by using a space warp. And then if you want to take things a step further, you can go in there and you can hand model the object by creating polygons, extruding faces outwards, bending things on a polygonal level, and doing basically polygon modeling and sub-D modeling. So primitives are only the basis of most models. They're not going to be the final thing, but they can be. And there's a world of options for you actually taking those primitives and making them into what you want them to be. So that's it for this chapter. In the next chapter, we're going to be looking at coordinate spaces, and it's important that we understand these and we have a good grasp on the concepts behind them and how to use coordinate spaces so that we can easily manipulate the primitives that we've seen here, and also so that we have good control of sub-objects such as vertices, faces, and so on, when we're doing mesh editing. So let's move on now and have a look at that.